Today, with a little bit of help from our calculator, we're going to sketch the graph of f of x equals 12x cubed plus 4x squared minus 3x minus 1. We're going to start off by going through the 5-step process that you see in the 4.1 PowerPoint, and then fill in the missing pieces using the calculator, because we probably would have needed some calculus to find out some of the things that we didn't find when we went through the 5 steps that the textbook gave us. We're going to start with step 1, but really you can kind of go out of order. You don't have to start with step 1. You can start with step 2 and then go back to step 1. Either any starting point in here for the steps would be fine. But I'm just going to start at step 1, which talks about end behavior of the graph. If you're talking about end behavior of the graph, you're really talking about the leading coefficient test, and then also whether or not you're looking at an odd degree or an even degree. So I'm going to have to look at my first term, which is a positive 12x cubed. So x cubed is my highest power, and that means that it is a third degree, which means that it's odd. And we know that odd functions have split end behaviors. So they're either one side's shooting down and then heading up from left to right, or maybe it started up high and then as it went from left to right, it ended down. Because it's positive, we know it's this one. So that if my x's went off to negative infinity, my y values go to negative infinity. And as my x values go to positive infinity, my y values go to positive infinity. So I know I'm pointing down here and I'm pointing up here. I also know that I have a certain number of turning points, right? So the turning points is always 1 degree less. So I'm doing something like this, possibly, but we don't know how high that peak is or how low that valley is. So really at this point, all I really know is this, the ends. I don't really know what's going on in between here yet. But I can find some important things like our x and y intercepts. So I'm going to go to step 2. So this is step 1. Step 2 says find the x and y intercepts. So it's easy to find the y-intercept. To find y-intercepts, you let x equal 0. So if x is 0, I get 12 times 0 cubed plus 4 times 0 squared minus 3 times 0 minus 1. So all of that for a negative 1. So I'm going to go to the other slide. And I'm going to go to the negative 1. And I say, I know I'm going through right here on my y-intercept. I kind of know like this side shooting down. And I know this side's shooting up. I don't really know what else is going on in between there. I do know that I could have a maximum of 3 x-intercepts in here, because the degree not only tells you the end behavior, but how many solutions that you can have. So I picked kind of a tough one. I'm going to need to factor this so that I can use zero product property to find the solution. So I'm going to scroll down a little bit, get this out of my way. And now I'm going to look for my x-intercepts, which is just really a solve. So where would this function be equal to 0 if I have 12x cubed plus 4x squared minus 3x minus 1? When you have 4 terms, you're probably going to want to try a factor by grouping. And this actually works out pretty nicely. If I split these so that I look at the first 2 terms and then the back 2 terms. The front 2 terms have a greatest common factor of a 4x squared. So I'm going to factor out a 4x squared from in here. 4x squared times 3x will give me back the 12x cubed, times a positive 1 will give me the 4x squared. If I factor a negative 1 out from the back 2, times a 3x will give me the negative 3x, times a positive 1 will give me a negative 1, and conveniently, I have a factor by grouping situation that both of those match. And so the greatest common factors are going to become the leftover for the big expression, and the 3x plus 1 will act as our greatest common factor. What it looks like is that you just kind of take those coefficients and put them in their own set of parentheses. But what often happens is that you have to do more than one step, maybe sometimes more than 2 steps, to factor completely. You can see here that I have the difference of 2 perfect squares, and that could be further factored into 2x plus 1, 2x minus 1. And now I have 3 unique linear factors. And I can take each one of these and set them equal to 0 using the zero product property and get my 3 solutions. That would be a negative 1/3, a negative 1/2, and a positive 1/2. And those are my 3 x-intercepts. So I'm going to go back to the first slide and put in my negative 1/3, which would be kind of like here. And actually, I'm going to make this a little bit bigger. I'm going to make the reds 1s so that we have a little bit of space. So that way he's a negative 1/3, he's a negative 1/2, and he's a positive 1/2. And those are my 3 different intercepts. Now, when you're talking about intercepts, you also have to talk about how does it intercept it. And that has to do with the multiplicities. If something has an even number of multiplicities, where that linear factor happens an even number of times. And so an example of that would be x plus 2 times an x plus 2 times an x plus 1, right? So this happens twice. And so I can use the shorthand of a square to kind of put that together and save myself some ink, right? So this would be an even multiplicity. Even multiplicities tag. They will go up to the x-axis, touch the intercept, touch the solution, and then duck back the other way. All of ours only appear once. And that means that is an odd number of multiplicity. So something that's 1s to the 1st power, to the 3rd power, to the 5th power. Those are odd multiplicities, and those are going to cut right through. And so evens tag, odds will slice. And so I know that now I'm coming up through this. So my arrow is not here, but wedged all the way over here. It's going to come up and go through this, do something, turn around, so it can cut through this maybe, do something down here, turn around, and then shoot up like this to cut through. And so that this piece that's up is all the way down here. So I have this little tightly squeezed in graph. Now I'm doing some guessing through here. I don't know how high this goes up. I don't know if it goes down like the way that I drew it this way or if it came through like this. Not really sure. But I know all of my graph kind of appears in this little small range between a negative 1/2 and a positive 1/2 right now. I have a maximum number of turning points. We know that since I have 3 unique intercepts that I'll have 2 turning points. And behavior near the x-intercept, that has to do with your multiplicities and where it's going through. And so I kind of have a sketch right now of what's going on. We would need calculus to find out where these turning points happen. So that's where I turn to my handy calculator. I'm going to type in my function, which was a 12x cubed plus 4x squared minus 3x minus 1. I'll hit graph and we'll see what we get. Oh, So it's hard to see, right? So we're going to use zoom. I'm going to zoom in, and I'm going to put Blinky right in the center there. Okay, we were pretty close. I'm going to take all of this off. I'll put my intercept back in. So you can see that it's coming up, but hardly at all, that you almost can't even see it. And in fact, if you click on Window and take my Y max to a 1, you can see it hardly even gets over the x-axis. So it goes like this. Beep. Comes down the way we thought. Not too low. Looks like it's just after the 1. Turns around and then comes back up. And so with the help of my graphing calculator to find maxes and mins, and the help of my steps from 4.1 to find what my behavior would look like and what the multiplicities are, I can get a good idea of what my graph will look like before I even plug it in. So had I maybe accidentally left off the 3 like I almost did before, you should know right away that there's a problem with this graph because my x-intercepts don't match what I know should happen because I already did the algebra. So you want to use some of your brain and some of your technology to counterbalance each other and help you from overlooking any errors.